Okay, so let's look at this very kind of illustrative graph, a very famous graph of the action potential. And so if you can see on the right axis, the right kind of up and down axis here, we actually have the voltage line. So this is the voltage scale. And you can see at the bottom, it says resting potential. And look over, the x-axis is actually time in milliseconds, so thousandths of a second, right? And the dotted line on this graph actually is referencing the y-axis on the right, the voltage. So you can see that at time 0, we're starting at minus 65 millivolts, right? And that is the resting potential. And then you can see the line sort of working its way up. 0 is up higher on that voltage axis. And what we're doing is we're moving it from minus 65, up towards minus 55. So we're depolarizing, right? This is showing it's being depolarized. So something is depolarizing, the cell that we're examining here. Remember that could be at a synapse, where glutamate or like an excitatory neurotransmitter is released, binds to a receptor here that responds by changing shape at opening channels that lets sodium pass through. Sodium will then enter, this neuron, basically because of the electrical force, opposite charges attract, and the concentration gradient force, things move from areas of high concentration to low, and you're bringing positive sodium from the outside to the in. So you're going to be, reducing the charge difference, right? You're going to be going from minus 65 at rest, to maybe minus, 60, and then you're going to hit, the threshold of minus 55, and then you can see this line just sort of shoot all the way up. It goes up to like positive 20. And then we're going to see it then drops very, very rapidly. It overshoots a little bit here, right? It goes a little bit below the resting potential, and then it works its way sort of back, to the resting potential. Now, the y-axis on the left side of the graph, right? That's called conductance, or G. This is the ion permeability. This is, basically a measure of, how permeable the membrane is to the flow of ions. How many ions are crossing the membrane, and you can see that the GNA plus, right, the conductance for sodium, right, at time 0 back here is pretty much, effectively 0. There are some of the non-gated sodium channels, right, that we talked about. So there's some leakage, but, to all intents and purposes, it's pretty much 0. But if you depolarize to threshold, look at that conductance. All of a sudden, it jumps way high, right, because this is what happened. Minus 65, right? Here is the voltage-gated, sodium channel, right? It's closed at the resting potential of minus 65, but when we depolarize that voltage line, right, to minus 55, to the threshold potential, it opens the threshold and swings open and allows for a ton of sodium, to cross a ton of conductance, right, of sodium through the membrane. But that halts after about a millisecond, right? Because you're suddenly at positive 20 in the voltage line, right? And the voltage-gated sodium channel closes, right? It closes in this form where it will not reopen now, until you get back to minus 65 and it can reset, right? So that sudden drop in the conductance, the passage of sodium across the membrane, has a lot to do with the drop in that voltage line, on the right axis here, going back from positive 20 back down towards, repolarizing towards the resting potential. But another significant contributor, right, is if you look at the conductance for potassium, for K+, right? Well, that, at minus 65, right, the voltage-gated potassium channels are closed. But at minus 55 at the threshold, if you've depolarized, right, you touch something, excitatory neurotransmitter or whatever, you've depolarized, from the resting potential of minus 65 to the threshold potential of minus, 55. Not only are the voltage-gated sodium channels opening, but the voltage-gated potassium channels are opening. And initially, potassium leaves, it leaves, but it leaves more slowly because the concentration gradient force wins, and the net flow is out. But the electrical force at minus 55, right, negative inside, it's a positively charged potassium ion, will tend to try to keep it in. So it goes out, but it goes out a little slower. But then with all that sodium rushing in, right, and changing the polarity, so it's now positive inside. Now the forces are aligned, right? It's the electrical force, potassium's inside and high concentration, and it's now positive 20 inside, right? So both the concentration and electrical forces will drive the potassium out. So the potassium leaves, goes out really, whoa, it's out, right? And as it does so, it also contributes to the drop in that voltage line, a sort of repolarization, back towards the resting potential of minus, 65. The other contributing factor here is, right, when all that sodium, here at minus 65, no sodium can get in because the voltage-gated sodium channels are closed. Minus 55, depolarized to threshold, it opens. All that sodium rushes in, and then those channels close, right? So now all this sodium on the inside is trapped, right? On the inside. It can't get out because those channels closed. But a little bit further down the membrane, right? It's at the resting potential, right? And that means like negatively charged, minus 65. It's a positive ion in here. It wants to go that way because of the electrical force, right? And it's also in high concentration because all that sodium just came in, right, to this location. Now it's trapped inside. So a little further down, it's at the resting potential, which means most of the sodium's on the outside, very little inside. So the concentration gradient force will drive it down too. And I want you to imagine if you hit minus 55 at the axon hillock, at the beginning of the axon, you can have all sorts of excitatory, inhibitory, depolarizing, hyperpolarizing connections up here. All sorts of ions crossing the membrane depending on the kinds of stimulation that this neuron is getting. Neurons can have up to 10,000 distinct synaptic connections here. There's a lot of kind of summating of all of these different ion changes that need to happen. But if you reach minus 55 at the hillock, there's a ton of those voltage-gated sodium channels that open, a ton of those voltage-gated potassium channels open. You initiate an action potential. And the sodium, which gets trapped when it comes in and the channels close, right? Well, it'll move down this way. And as it moves into this next location here, right, it's going to depolarize that next segment of the membrane to threshold, to minus 55, and a whole bunch more voltage-gated sodium channels and potassium channels are going to open. So you're going to get sodium in, potassium out, right? And then it's going to go down further. Sodium in, potassium out, sodium in, potassium out, sodium in, potassium out. It's going to work its way all the way down, to the very end of the axon, where that arrival of depolarization will result in the release of neurotransmitter. So we'll talk about this more in class. This is mostly meant as kind of review for those of you who've watched, the overall, recorded lecture. But anyway, this is a very famous graph that sort of summarizes the action potential.